Okay, so hello everyone. Welcome to this live problem solving session for the course Introduction to Galois Theory, which is instructed by Professor Krishna Hanumanthu. So we are almost at the end of this course, and this is the week 7. So as usual, I will be solving some problems uh, related to the contents of week 7. So before that, let's briefly recall the topics of week 7. So in this week, we mainly our main goal is to prove the insolvability of the quintics. So before that, we started with characterizing the solvable elements. So in the previous week, we have defined what do we mean by solvable elements, and in this week we started with a characterization of that. So basically, it's a group theoretical characterization. So characterization of solvability. So basically, when an element, let's say alpha, belongs to a field which is subfield of C, is solvable. So we have seen some group theoretical characterization for this. Then we basically wanted to study the Galois groups of polynomials. So that will help us to prove that polynomials of degree less equals to 4 are always solvable. So for this, to find the Galois groups of various polynomials of degree less equals to 4, we have defined something called discriminant of a polynomial. And we have also written down the formula to compute the discriminant of a degree 3 polynomial. So formula to compute the discriminant of a cubic polynomial. Then we have listed down several results such as the Galois group of a polynomial is a subgroup of Sn where n is the degree of the polynomial. Second one is f is irreducible over f if and only if its Galois group over f is a transitive subgroup. So Galois group over f is a transitive subgroup. Transitive subgroup of Sn, and also using the discriminant, uh, we have proved that this Galois group of the polynomial f will be subset of n. We have given a characterization using the discriminant of the polynomial. So square of if this element is a square or something like that, then it is a subgroup of the alternating group. Otherwise, it is not. Then we have give description for the Galois group. So description of Galois group of a polynomial when degree of f is 1, 2, 3, and 4. So for 4, there are lots of possibilities. So for that, to give description for a degree 4 polynomial, we have defined something called resolvent cubic of that polynomial. Then we have used the characterization for a degree 3 polynomial to give the description of the Galois group of degree 4 polynomial. So finally, this leads to the fact that if f belongs to fx, where f is a subfield of C, and degree of this polynomial is less equals to 4, then f is solvable. So a polynomial of degree less equals to 4 is always solvable by radicals, but this is not true for degree at least 5 polynomials. There are polynomials of degree 5 which are not solvable by radicals. So to prove that part, to prove that insolvability of quintic, uh, we need to define other things. So this is a topic which we have started doing, the solvable groups. So in this we have seen the definition of solvable groups. Uh, Basically the existence of such a tower, and then we have seen several examples like Sn is not solvable for n greater equals to 5 because n is simple for n greater equals to 5, and Dn, the Diedel group, it is solvable, and I think abelian groups are solvable. That's trivial thing. Those kind of things we have seen, and we have also seen some other theorems. So like subgroup of a solvable group is solvable, homomorphic image of solvable group is solvable, subgroup and homomorphic image of a solvable group is solvable, and the converse is also true in some sense. Like if we have a subgroup H such that H and the quotient is solvable, then it will imply G is itself solvable. So in solvable groups we have studied these things which we need to prove insolvability of quintics. Then we have defined composite of fields, which we have not done earlier, but we should have done. So composite of fields, and we have seen several theorems related to this, like composite of Galois, what will be that? Composite of radical extensions, what happened to those things? So composite of Galois extensions and radical is Galois and is also radical. Then we have mentioned the main achievement of Galois, who translates the this problem of solvability into into a group theoretical problem. So that main theorem of Galois, so which states that a polynomial is solvable if and only if its Galois group is solvable. So a polynomial is solvable. So of course we have assumed that the characteristic of the field is 0. So if and only if the Galois group of F over F is solvable. So this is the main achievement of Galois, and I think these are the all the topics of this week 7. Okay, so let's move on. So we have seen how to define the discriminant of a polynomial, right? But we don't know much about how to compute the discriminant. So let us talk about those things. So actually there is an efficient way to calculate discriminant of a polynomial. So I want to mention that way, and maybe I will do one example to illustrate that. So in order to mention that method, I have to define something which is called resultant of two polynomials. But I don't need a general definition, so I will go to the general facts directly. So let's write down the things. So there is an efficient way to compute the discriminant of a polynomial. So so let fx belongs to fx, where f subset of c be a polynomial, and let alpha 1 up to alpha n, maybe I will write down as the definition. So let it is, so I need the monic polynomial. So let f be a monic polynomial, and with roots, let's say alpha 1 up to alpha n, because it's of degree n, so it has n roots, alpha n. Then uh, the resultant of, okay, so let me write down this as a fact because I am not using the general definition, so I will just directly write down the results. So the first thing, the resultant of f and f prime is basically denoted as r of f comma f prime, and it is basically the product of the of f dash, means the formal derivative at the roots from I equals to 1 to n. So f dash is formal derivative. So we know that f equals to xn a n minus 1 x power n minus 1 plus dot dot a1 x plus a naught. So then f dash will be n x power n minus 1 plus n minus 1 times a n minus 1 x power n minus 2 plus dot dot a1, this thing. So just the usual derivative, it has no other meaning. So this is called the resultant. And the second thing is, the discriminant of f can be written in terms of this resultant. So discriminant of f is basically minus 1 power n into n minus 1 by 2, where n is the degree of f, that we have already mentioned, it's x power n, times resultant. So basically, to compute the discriminant, we have to compute this resultant of f and f prime, and also and to compute this resultant, we need to know the roots of this polynomial. And if we don't know the roots, then also it can be computed in using some theories. So yeah, so this is the formula for the resultant that I will use. This is not the general definition, because I don't want to use that one. So maybe let's do one problem. Okay, so this is the first problem. So let f be the polynomial defined by uh, x power n plus n times x power n minus 1 plus n times n minus 1 times x power n minus 2 and plus so on, n times n minus 1 dot dot 3 2 times x plus n factorial, right? Then find the discriminant of this polynomial. So how to find the discriminant of this polynomial? So in general, we know the definition of a discriminant. So right, so in general, if okay, I should write black. So if alpha 1 up to alpha n are roots of f, then by definition, the discriminant of f is basically the product of alpha I minus alpha j square, where I is less than j. Right. So this is the definition that we know. But to know the discriminant, to find the discriminant using this definition, we have to compute the roots, right? And also to compute the resultant, we also need to compute the roots in sometimes, but that's another way. But if we directly want to compute the discriminant using the definition, we have to compute the roots compulsorily. But what I want to do is I want to use the this formula using the resultant. So let's see how to do this. So first I will compute the resultant. So to compute the resultant, we have to compute the derivative first. Okay, so let's do this. So it is just n times x power n minus 1 plus n times n minus 1 times x power n minus 2 plus dot dot. It is it is just n factorial. So if you compare now, if you just stare at these two polynomials fx and f dash x, then you will realize that you are just missing the leading term here, right? So it is basically just fx minus x power n. So we have got a relation between fx and f dash x, which is fx equals to x power n plus f dash x. Now let's use this to find the result. So what is resultant of f and f dash? It is basically product of f dash evaluated at alpha I, from I is from 1 to n, where uh, alpha 1 up to alpha n are the roots of f. So so now note that, so if alpha I is a root of f, so this will imply f of alpha I is 0. So now let's use this equation. So it will imply f dash alpha I is minus alpha I power n. So this product is basically product of minus alpha I power n, I is running from 1 to n. So we can take minus 1 power n out, and this is product of alpha I power n, where I is from 1 to n. Now alpha I are the roots of the polynomial. So this we can write it as minus 1 power n product of alpha I whole power n. Now we know that how to find the product of the roots using the coefficients of the polynomial. So there is a formula for that. So this is basically minus 1 power n is as it is, and this thing is minus 1 power degree and the uh, constant term. Okay, so I will write it is just n factorial. So product of the roots of the roots of the polynomial, let's say an x power n plus a n minus 1 x power n minus 1 plus dot dot a1 x plus a0 is basically minus 1 power n a0. Okay, so there is a formula in theory of equations, you might have seen this. So let's use this because the constant term is n factorial in our case. So a0 is n factorial. So we have found the resultant. without knowing the roots of the polynomial, we have found the resultant. So what is the discriminant now? So discriminant of f is minus 1 power n times n minus 1 by 2, where n is the degree, times the resultant. So this is minus 1 power n times n minus 1 by 2, again minus 1 power n, again minus 1 power n factorial, whole power n. So what will be this? So minus 1 power n whole power n, it will be just 1. Okay, so basically this term is 1 because n times, okay, it is n times n minus 2. Okay, so let's write this. This is minus 1 power n times n minus 1 by 2, it will be as it is. But here we have n plus n square times n factorial whole power n. But n plus n square, it is always even because it is n times n plus 1. So to product of two consecutive numbers is always even. So this part is just 1. So we have minus 1 power n times n minus 1 divided by 2 times n factorial whole power n. So this will be the discriminant of the polynomial. So using the formula for the resultant, uh, without knowing the roots, we have computed the discriminant of this polynomial. Okay, so yeah, so maybe you can do other more examples from the books. So okay, now let's do some other problem. So we have already done cyclic extensions, right? But in characteristic P for finite cyclic extensions, there is one characterization of that. So let's do that one. So it is the structure of cyclic Galois extensions over characteristic P. So structure of cyclic extensions over positive characteristic. So these are mainly known as Artin-Schreier's extension. So Artin-Schreier extension. So let's see what it is. Okay, so let E over F be a cyclic extension of degree P. and characteristic is also P. Then this E has a particular structure. Then this E has to be of this form equals to F alpha, where this alpha is a root of the polynomial x power p minus x minus a belongs to fx. Means this a is in fx. So we already know that finite extensions of finite fields that are cyclic, right? But here the characteristic of f is p. That does not mean that f is a finite field. So it is just a field of characteristic p, and we are taking an cyclic extension of degree p. Then we are saying E has this structure. If is a finite field, then it is clear has this form, but this alpha may not be a root of a polynomial like this. So this is a special kind of extension. So let's see how to prove this. So we need to prove two things, that E is a primitive extension of F, or E is a simple extension of F. So what does that mean? That it can be generated over F by a single element. That is the first thing we have to prove. Then we have to prove that this generator alpha is a root of a polynomial of this kind. So that is the second one. So let's do the first one. So note that E over F is a cyclic extension. So let G be the Galois group of E over F. Right? Then this G has to be a cyclic group because E over F is a cyclic extension. So then this G has to be generated by some sigma, because E over F is a cyclic extension. Now using this automorphism sigma, we will define a function. So define t from E to itself by t of a is sigma of a minus a. Then you can check that this t is a F linear transformation. So you can verify this. So I am leaving this as an exercise. So as it is a F linear transformation, let's see what is the kernel and what is the image of this linear map. So kernel of T is basically all those elements of E such that T of A is equals to 0. But that means all those elements of E such that sigma of A is equals to A. Right? So this is basically the fixed field of E uh, of sigma, and this is basically F, because E over F is Galois. Okay, so I should write one more line, because this is same as E over G. And this is same as F. I should write this thing here. So the kernel is the base field F. Now T is a linear map from E to itself. So we can compose T with itself, right? Then again it will be a linear map. So what is T power P? So T power P is basically sigma minus identity whole power P, but we are in characteristic P. So this is just sigma power P minus identity power P, and which is same as sigma power P minus identity. And what is the sigma power P? This has to be identity, because sigma power P equals to 1, because cardinality of the Galois group, which is order of sigma, is P. This is P because this is same as the degree of the extension, and we are in a Galois extension. So T power P is a zero linear map. So what does this mean? So this means T composed T power P minus 1 is 0. So image of T power P minus 1 is contained in the kernel of T, which is F. Right? Now my claim is this image is exactly equals to F. So note that image of T power P minus 1 is either 0 or F. Why? Because image of T power P minus 1 is an F vector space, and it is a subset of F. So dimension of image of T power P minus 1 over F is either 0 or 1. So if it is 0, it has to be the 0 subspace. If it is 1, it has to be the whole F. There is no other choice. It cannot be 0. So this will imply image of T power P minus 1 is equals to A. Why? Because image of T power P minus 1 cannot be 0. Because if it is 0, image of T power P minus 1 is 0, that will imply T power P minus 1 is 0. Right? And this will give sigma minus 1 power E whole power P minus 1 is 0. But if we expand this, by expanding this, we will get a non-trivial F-linear combination of, so F-linear not combination, relation of sigma power P minus 1, sigma power P minus 2, and dot dot 1. But these elements are linearly independent by Dedekind's lemma, which we have done before starting the Galois theory, uh, maybe in the first or second week in the character theory. So which contradicts Dedekind's lemma. So we know that different characters are linearly independent. So in particular, different field homomorphisms are linearly independent. So image of t power p minus 1 cannot be 0. So image of t power p minus 1 has to be f, and which is same as kernel of t. So image of t power p minus 1 is f. So it will imply 1 belongs to f, which is image of t power p minus 1. So let a belongs to e such that t power p minus 1 of a is equals to 1, and let t power p minus 2 of a is equals to alpha. So then 1 is equals to t of alpha, and which is same as sigma of alpha minus alpha, right? So this means sigma of alpha is alpha plus 1, and if we apply again sigma, so sigma power I of alpha is alpha plus I for 1 less equals to I less equals to p minus 1. So this implies alpha is not fixed by sigma square dot dot sigma power p minus 1. So alpha is not fixed by the Galois group, any element of the Galois group, any non-identity element of the Galois group. So E has to be f of alpha. So observe that this is a technique to find the primitive element. You just find a element which is not fixed by any non-identity element of the Galois group. Then that element will give you a primitive element. So we have proved the first part. So we have constructed a primitive element for this extension. Okay, now we have to prove that this element is a root of a special kind of polynomial. So this proves the first part. Okay, now we have to prove the second part. So what we have to do, we have to prove that alpha is a root of the polynomial x power p minus x minus a for some a belongs to f. So let's prove this. Since sigma of alpha power p minus alpha is same as, so this is same as sigma of alpha whole power p minus sigma of alpha, and we know the image of uh, so image of alpha under sigma is alpha plus 1, that we have already find. Let's use that. So it is basically alpha plus 1 whole power p minus alpha plus 1, but we are in characteristic p, so this is alpha power p plus 1 minus alpha minus 1. So this is alpha power p minus alpha. So alpha power p minus alpha is fixed by sigma. So let's take a as alpha power p minus alpha, and this is belongs to the fixed field of e power sigma which is same as fixed field of e power g, fixed field of g, and which is same as f. And alpha is a root of x power p minus x minus a because of this relation. So this completes the proof. So a degree p cyclic extension over a characteristic p field is of this particular form. This we already proved. Okay, so now maybe we can talk about the composite of fields little bit, because we have not done much about that composite. Okay, so let's see what we can do. So I will just do these things as problems, but these are merely results. Okay, so okay, first let me draw this. Okay, so let K be a field. So we are taking a field K, and we have and E, comma F are subfield of K bar. K bar means the algebraic closure of K. Right? Now, since E and F are subfield of a bigger field, we can talk about the smallest field which contains both E and F. Right? This is denoted as E times F. This is the composite of E and F. So this is the definition. Smallest field containing both E and F. So we have E here and we have F here, and we have E intersection F here. So we have a tower of this kind, and again we have EF here, which is the composite. So thus now the result says that the first one, E over K is Galois it will imply EF over F is Galois. And the second thing is E over K and F over K are Galois. This will imply the composite is Galois over K. So if this extension is Galois, then this extension is Galois. This is the first statement. And if this one and this one is Galois, then this bigger tower is Galois. So I think this second part we have proved, I think, in the lectures, but maybe we can do it here also. So both the things are actually easy, or rather straightforward. Okay, the second one has also one more part, maybe I should mention. This is Galois, and the intersection over K is also Galois. So this is a non-trivial part. And this we have not done, I think. Okay, so let's see how to prove this. So first, let's prove the part A. So E over K is Galois. So that will imply E is the splitting field of a separable polynomial, let's say F over K, right? That is the one of the equivalent conditions for the for extension to be Galois. So now F is separable over K also, because separability means just having distinct roots in some splitting field. F is separable over F, because here we have F, here we have K. So it is separable over the smaller field, it will automatically imply it is separable over the bigger field. So since EF is the splitting field of F over F, EF over F is Galois. Because E is already the splitting field, but we are taking the polynomial from F. So we have to consider the elements of F also. That's why we are adjoining F. But we need to consider the smallest possible such field. So that is the composite. So it has to be the splitting field of F over the base field F. So it has to be a Galois extension. So this part is very straightforward. Now the second one. Now let both E over K and F over K are Galois. Then we have to prove that the composite and the intersection both are Galois. So one part is also straightforward. So then E is equals to some splitting field of let's say F over K, and F is splitting field of G over K. Then okay, F and G are separable. That also we need to assume. Then check that E over F is the splitting field of the separable polynomial F times G over K. So this will imply EF over K is Galois. So this part is also straightforward. Now we need to prove that the intersection is Galois. So E intersection F over K is Galois. So for this, I will use another characterization of Galois extensions. So it is sufficient to prove that it is normal because separability is not an issue. Because we know that separability is transitive. So it is sufficient to prove that E intersection F over K is normal. Okay, so let sigma from E intersection F to K bar be a K automorphism. Now what do we have to prove? So to prove E intersection F over K is normal, we have to show sigma of E intersection F is contained in E intersection F. Now let's draw the picture. So here we have K, here we have E intersection F, here we have K bar, and we are taking this map, but we can extend it to the composite by the extensions theorem. So now by the extension theorem, we can extend sigma to sigma bar from EF to K bar, right? And this is a K automorphism. Now since EF over K is Galois, so sigma bar of, okay, we don't need EF, okay. Okay, so let's do the other way. So we can do it for E and also for F. So since E over K is Galois, so sigma prime of E equals to E. Similarly, by extending sigma to sigma double prime from F to K bar, we get sigma double prime of F is equals to F. So this will imply sigma of E intersection F is subset of sigma of E intersection F, because both are subset of E and as well as F. So this completes the proof. So it is normal, hence it is Galois. Okay, as these are Galois, maybe we can talk about the Galois groups also. So this is problem number 4. Okay, so so again we are in the same setup. E is here, K is here, F is here, EF is here over the K bar. Here it is K. So let E over K be a Galois extension and F over K be a finite extension. Then from the previous thing we know that so this part is Galois implies this part is Galois. Right? So then show that the Galois group of EF over F is isomorphic to the Galois group of E over E intersection F. So E over K is Galois. So E over E intersection F is also Galois. So it will lie something like here. Okay, let's not draw this one. It's not looking good. So let's prove this. So it's not difficult. So note that we have an obvious map. So we have an obvious map, let's say phi, from this Galois group EF over F to the Galois group E over K, defined by the restriction. So phi of sigma is sigma restricted to E. So sigma fixes F and K is subfield of F. So sigma also fixes K. So it is well defined. Now check that phi is an 1-1 group homomorphism. So that part is easy. Right? But what is the image of phi? Now let's determine the image of phi. Okay, so let H be the image of phi. So then H is a subgroup of the Galois group of E over K. Now, what are the things that are fixed by this sigma? Sigma fixes F, but we are restricting it to E. So sigma has to fix elements of F which are in E. Now, sigma belongs to Galois group of EF over F implies sigma fixes F. So, sigma restricted to E must fix E intersection F. So, so this will imply that clearly image of phi has to be Galois group of E over E intersection F. So if you want, you can give much more rigorous arguments, but I think from this it can be seen. So this will give Galois group of EF over F is isomorphic to Galois group of E of E intersection F. So this is all about the composite which I wanted to do. There are some more things which can be done, but let's not involve all the things. So if you're interested, you can refer to any standard book and you will find all the details. So maybe we can stop here for today. Okay.